Today, on behalf of my co-authors, I'm here to present our research, cataract detection and grading using ensemble neural networks and transfer learning. I'm Renato R. Maaliw III from the College of Engineering of Southern Luzon State University from the Philippines. For the introductions, cataracts are one of the primary cause of visual impairment and blindness. So for this research, we will categorize and detect cataract in terms of five categories from normal to severe. So based from statistical data, there are 295 million worldwide that suffer from this condition. And by 2025, it is projected to add more 43 million instances due to wide range of lesions and eye tones, dimension, and the overall structures and positions in the retina. Cataract detection is a challenging task. So traditional methods are provides an easy experience to patients because of its intrusive nature. There are many obstacles related to fundus images for cataract assessments. Numerous research has relied on complex, labor-intensive, and manual feature extraction for cataract detection and classification. Moreover, ophthalmologists have varying evaluations, even with considerable knowledge and experience. These are all rooted on subjectivity. So, as a solution, deep learning gained prominence in the science of computer vision and image processing in the past years. However, based on our literature, we noted that the number of existing methods have limitations in terms of identifying cataract vascular feature using only traditional machine learning techniques. So for this research, we will contribute to the science to the development of a new strategy to locate the eye's vascular features with precision. By taking into account the long distance dependencies of the fundus images, we can improve the cataract identification with five baseline classification with the help of transfer learning and hybrid neural networks. So our pipeline can support eye experts in the reliable diagnosis of cataracts with minimal physical involvement. So for the methodology, so we acquired 2,500 high-resolution fundus images from various cataract retinal archives. So these are professional labeled into five categories from normal to severe. So for the pre-processing, so we discovered that the green channel, the green color space, produces a lot of details for cataract feature extraction. So all input images are converted into green channel color space. So in order to have big sets of data, so we provided geometric modification through resizing, rotating, shifting, and flipping to obtain more 10,000 data for a total of 12,500 training images. So we use tenfold cross validation with 80 to 20 training and testing set split. So for the overall mechanism of the transfer learning, so our input images are divided into 16 patches that is fed to various CNN models to extract the retinal features. So we use global average pooling, then combines the derived attributes, which is 25 attributes, and we image-wise classified by using a stack long short-term memory networks in terms of both detection, normal to cataract, and grades from normal to severe. So here are the top four convolutional networks. So we utilize AlexNet, Inception V3, Exception, and Inception ResNet V2. So for the block diagram, so we have a global average pooling 3D, a dense layer with 500 hidden, then batch normalization, and another dense layer with an activation of rectified learning unit. So only the inception ResNet v3. So we provide a dropout of 0.03. So what is the image-wise method? So for the image-wise method, so we use the stacks of recurrent neural networks, which are LSTEM. So to provide a context-aware learning. So by using not just unidirectional LSTEM, the performance is improved because bidirectional LSTEM traverses sequence with both forward and backward orientations. So as you can see, these are the structure of the bidirectional LSTM and our stacking configuration. So we use sequential based hyperparameter optimization for the derivation of the optimized hyperparameter for each neural network. So as you can see at the table, from learning rate to a GPU environment. So for the stack LSTM for cataract detection, so here are the hyperparameter optimization for the detection and grading. So for the ensemble techniques, so ensemble really minimizes the variance and bias by assigning weights to the attributes. So each weight for the models, it reflects individual contribution to the final output. So we utilized weighted ensemble algorithm with weights that are not predetermined and linearly combined. So for the evaluation criteria, we use the accuracy, precision, recall, specificity, and the Matthews correlations. So for the result, so what are the effects of layer stacking? So of course, when we stack LSTM, it required more time to reach equilibrium compared to lesser stack. We also observe that the primary layers of the stack, the first and the second, enhances the model's performance. And a pattern of steady diminishing number of neurons for each layer is beneficial for understanding the overall structure of the input image, as you can see on the convergence loss plots. For the ensemble modeled weights that we derive, so Inception ResNet V2 contributed a lot with 52% and 45% in terms of weights. So this is because the Inception ResNet V2 has residual connection, and it's very essential when dealing with nonlinear patterns such as the fundus images, while the AlexNet imparts the least contribution with both detection and grading. So for the cataract detection performance, this is a normal versus the presence of the cataract. So as you can see, the ensemble model trumps individual models with the overall accuracy of almost perfect of 99.20%. The AlexNet ranks last with 94.60%. For the cataract grading, still the ensemble is superior with 97.76 accuracy, while the AlexNet performs with a at least respectable accuracy of 94.44%. So we also analyzed the confusion matrix. So most of the prediction error came from the combinations of prediction from pronounced severe, normal mild, mild to moderate, and moderate to pronounced. Any other combinations that are not written here have zero occurrences of prediction error. We also analyzed the training and validation loss accuracy. So we observe an increasing convergence at epoch 60 to 100. We notice stabilization at 115th epoch and the gradual convergence at 80 to 100 with the highest training accuracy of 98.77 at the 106th epoch. We have also attained the highest validation accuracy of 98.68%. So based from the graph, there's no overfitting and underfitting based on the plots. So the study proved that the adaptive capacity of compounded pre-trained convolutional neural networks, stacked LSTMs, and transfer learning in boosting the performance of cataract diagnosis and grading. So our empirical results show that the ensemble model transcends other single models with a prediction reliability of 99.20% for the detection, and 97.76% for classification. The pipeline cuts identification and categorization error by an average of 2.55% and 1.79%. So of course, as with any research, there are challenges because there are noisy and insufficient image quality of fundus images that contributes to classification divergences or error. So as a limitation, this study did not investigate in offsetting these issues such as image enhancement and reconstructions. For the conclusion and future works, so really cataract is the foremost contributor to blindness or visual impairments. So if left untreated and undiagnosed, it can lead to permanent blindness. So most traditional procedure for cataract detection and grading is time consuming. It is a mechanical practice with vulnerability to disparities. Diagnosis is very difficult using only the naked eye due to the sometimes inadequate quality of fundus images. So we develop a minimally invasive end-to-end pipeline for identifying and classifying cataracts, leveraging ensembles of pre-trained CNNs and stacked LSTEM classifier with transfer learning and data augmentation. So based on our test, the ensemble is accurate and its coherence between the expert evaluation against our machine learning models resulted only with minor deviations. So we for the overall contribution of research, so we contributed to the advancement of deep learning medical image analysis by developing a sound and streamlined approach for the automatic recognition and grading of cataracts. This research has the potential to improve the clinical practice in understanding cataract severity and their treatments. So for the future work, we like to incorporate image enhancement techniques and also benchmark other convolutional neural networks in the future to improve the performance further of the pipeline. Thank you very much for listening.